Hi everyone, it's Mr. Zhang. Today we are going to be working on fission versus fusion and E equals mc squared. Okay, so I'm going to talk about Einstein's famous equation here and how we use it. Okay, so let's see here. Okay, so I'm just going to start by reading. So the following nuclear equation describes the first fission reaction ever discovered in the 1930s. So we have a neutron that is coming in, gets captured by uranium, and then it splits into two. I believe that's barium and krypton. Okay. On your left side, you have what's called the reactants. Okay, reactants. And on your right side, you have your results, your products. Sorry, your reactant and products. And you might know this from chemistry. Okay, so N is for a neutron. The above chart shows the rest of the masses of the participants in this reaction. Okay, so this is giving you the rest mass, and then here it's telling you the particle. Cool. Why will we use the word fission to describe this reaction? Well, that's because uranium-238 splits up. We could say the nucleus splits up. Okay, splits up. Sorry, I'm sick. Okay, then it says, calculate the following masses in atomic units. U. The total rest mass of all the products, the total rest mass. Okay, and the change. Okay, so what it wants us to do is, basically you want to add one side, right? So you want to add the masses of the reactants together on one side, and then add the products. Okay. So I'm gonna zoom in here. So what we're gonna do is, okay, so we have 1.009 plus 238, 238.0508, and that gives us, I need a calculator. Give me 1 second. Okay, so if you do 1.09 plus 238, so you want to keep all the numbers here because they might be important, and you'll see that there might be a little difference here. Okay, so that's what I get, and the unit for this is going to be, I think they want us to write this in U. Yes, unit U, right here. Okay. Okay, now, well, I think I did that backwards. Sorry, I think I did the products first. Whoops, my bad. So this is, we're supposed to do the products first. I did the reactants. So here's the reactants. And then for the product, it would be 144.927 plus about 94, approximate. Okay, and that gives us 238. Oops. 238.927 U. Okay, so the change in the mass during the reaction, you should get something like 0.1328 U. Okay, so does the fission reaction gain or lose mass? So in this case, does it gain or lose mass? Let's think about it. So we have, okay, so we have the reactants number, and then we have the products number, and we can see that we're comparing 239 to 238. Okay, so we can see that the mass, let's say mass of product, mass of the product is less than the mass of reactants. Okay, So we're comparing 238 to 239, and so we can say that the mass of the product is less. Okay, so the question kind of becomes like, what happened to the mass, right? That's the question here. Okay, so let's look at nuclear fusion reactions as well, and the question we're asking here is like, what kind of happens? So here we'll say it loses mass. Okay. So we're kind of thinking about, okay, what happened to the mass if it loses mass? And does the same thing also happen in a nuclear fusion reaction? Right, so here we can see that these two helium-3 are fusing together to make helium and two hydrogen atoms. Okay, so why would we use helium-3 combines? Whoa, that's not how you spell combine. Combines to make helium-4. Right. So the nucleus is getting bigger. Nucleus getting bigger. That's my Discord. Discord, get out of here. Okay. Let's see. Producing fusion reaction requires high temperature. Why? Well, let's see. What did I say? I'm thinking that it's because of charges, right? So to fuse, overcome charges, and we could say, to overcome charges. Okay, so you need them to be fast moving. Need fast moving particles. I shouldn't say. We should say isotopes. Right, so they have to be moving fast, and they have to overcome charges, and that's really what high temperature means, right? These particles are moving very fast. Okay, so then it says to calculate the masses in the atomic units, U. Okay, so we're going to calculate these. Again, so the mass of the products and the mass of the reactants. I don't like how there's barely any space here, but if you do this calculation, you should get, here you should get 3.0, is this right? Wait. No, I don't know why I said 3. You should get 6.0166U, okay? And then here, you should get 6.032U, something like that. And if you subtract them, alright, let's say you subtract these two numbers. Alright, so this one and this one, you should get a negative number, which is 0.0162U. Alright, so you got to use this chart here, in case that was not clear, to do these two calculations, to do these three calculations. Okay, so some mass is lost again. Okay, so similar to nuclear fission, some mass is lost again. So the question kind of becomes, again, what happened to the mass? Now you might anticipate, already what happened to the mass. I already did this on paper, by the way. We're gonna say loses mass because we got a negative number, right? Because the mass of the products is less than the mass of the reactants. Okay. As it turns out, although the mass and charge are conserved in nuclear reactions, energy and mass are not conserved individually. However, mass and energy can be turned into one another according to Einstein's equation. Okay, so while I was talking about this mass being lost, you might have already anticipated that some of this mass was turned into energy. Okay. Where E is energy, M is mass, and C is the speed of light. When nuclear reactions occur, significant measurable mass change of the nucleus occurs. I call that delta M. Delta M, okay? Einstein's famous equation is actually more written like this. Is used to by physicists, I suppose, used to convert nuclear mass into energy, and they can be expressed in different ways, as in units, as in we're talking about units here. Okay, you should already be okay. So for the HL kids, you should already be familiar with kilograms and joules, right? Mass is measured in kilograms, and then energy is measured in joules. It is more common when dealing with small amounts of energy to use the unit electron volts, or EV, and the mega electron volt, MeV. What is an electron volt, you might ask? Well, it is the energy that one electron acquires when it accelerates through a potential difference of 1 volt. Okay, so if you apply 1 volt to an electron, that and the energy that an electron gets is 1 electron volt. Okay, which, right, if you remember for the HL kids from the electricity unit, or from your previous unit, you remember that when you have a voltage times a coulomb, you get, right, so when you have E, right, electrons measuring coulombs, multiplied by volt, you get a joule. So therefore, 1 EV is equal to this many joules, which is very, very tiny. It's to the negative 19 power. Very, very tiny. Okay, so I'll take a look at this table here. You can look at this by yourself. But what's important for you to know here is that the atomic mass unit, which used to be AMU, is 1/12 of carbon-12, which I'm kind of like, what? What does that even mean? Right? I'm kind of confused about that. But here's the information that you need. Okay, so the information that you need to know is that 1U is equal to 1.66 times 10 to the negative 27 kilograms. Okay, so if we want to use Einstein's equation, right, we always have to convert to kilograms. And the other thing that you should know is that 1U is equal to 931.5 mega electron volts. Okay, so now on page 3, and you guys can do this yourself, it's going to ask you to calculate using E equals mc squared. So I think what I want to do is show you one, but really it's just, you just plug in the numbers and you figure out what it is, right? So let's do this in joules, and you could also do it in electron volts as well if you want, but we're going to do it in joules. Okay, so using this equation, E equals mc squared, so it wants us to calculate the energy that is released in the decay of a neutron. And so you want to do 0.08665, and you want to multiply that by the conversion factor, right? So we want to convert it. Right, so we got to convert it first. Then we'll multiply it by the speed of light, which C is equal to 3.00 times 10 to the 8 meters per second. Meters per second. I think, yeah. It's not meters per second squared. Because we're talking about the speed of light. Okay, times C squared. Alright, so when you do this multiplication out, it will give you the amount of energy in joules. So the energy that we get, that I got, and you can check it. I believe is something like What did I get? What did I get? What did I get? Okay. I did not do a good job writing this down on paper, but I think I got 1.5064 times 10 to the negative 10 joules. Okay, so when you do, so you want to calculate them and then you want to subtract them, and what you should get is that there is a difference in the energy, or yeah, you should get that there is a difference in the energy, right? Or also the idea that 1.25 times 10 to the negative 13 joules of energy is released. Okay. Alright, okay, so I think that's really all you need to know to be able to do the rest of them. It's kind of tedious, you know, just try to keep all the sig figs so that your numbers are more precise. But yeah, otherwise, yeah, because we need to have all the numbers there to see a big difference. Okay, so that's it for this video. Hopefully it was helpful. Good luck. Miss Getz and I probably won't be there. I won't be there because I'm sick. Alright, see ya. Bye.